Welcome to our lecture on Chapter 7 for MEC410 Design of Machine Elements. My name is Jay Mendelson. I'm a lecturer in the Mechanical Engineering Department. This week we're going to study belt drives and chain drives. Our reading is Chapter 7 in our book Machine Elements in Mechanical Design, 6th edition. For our homework problems, we have V-belt drive problem 21 from the textbook, where we're asking you to select a sheave, otherwise known as a pulley, from page PT 7-29 of the Balder catalog using the link shown. And we're going to ask you to select a V-belt from the Granger catalog using the link shown. We have roller chain problem 41. And we also have a timing belt problem for you to work on using this input data. For power transmissions, we have power screws that converts rotations into translations. And many applications require the transmission of rotational motion, sometimes over long distances, and usually changing the speeds of rotations. Belt drives, chain drives, and gears are designed for this purpose. In the lower right corner, you see a transmission with gears. In the lower left corner, you see a V-belt drive. And in the middle, you see a chain drive. Belts and chain drives are known as flexible transmissions. A belt drive connects two or more wheels, called pulleys or sheaves, with a belt. And that belt is not rigid, hence the name flexible transmission. A chain drive connects two or more tooth wheels called sprockets with a chain, which is also a flexible transmission element given that the chain can sag, but it does consist of rigid pieces. And flexible elements are often used instead of gear drives to deliver power over relatively long distances. V-belt drives transmit power at high speed, low torque, and over long distances. V-belts power the radiator fan and alternator on gasoline engines in autos at linear speeds between 2,500 and 6,500 feet per minute, ideally at 4,000 feet per minute. At lower speeds, the tension in the V-belt becomes too large for typical V-belt cross-sections. At higher speeds, dynamic effects such as centrifugal forces, belt whip, and vibration reduce the effectiveness of the drive and its life. Chain drives transmit power under low speed and high torque, basically the opposite of V-belt drives. And as you know from riding a bicycle, you have one, and you also see them on motorcycles and tanks and all kinds of conveyor belts. They're easy to install and uninstall, and you don't need to move the sprockets to replace the chain. But at very high speeds, noise caused by impact between the chain links and the sprocket teeth become very irritating. You can use both V-belts and chain drives in systems where you use a V-belt drive operating at fairly high speeds in the first stage between the electric motor and a pulley, and in the second stage where the speeds are lower, you might use a chain drive. A belt is installed tightly on a set of pulleys, or sheaves as they're called, and when used for speed reduction, the small pulley is mounted on the high-speed shaft, otherwise known as the motor shaft, while the larger pulley is mounted on the driven axis. And the belt is installed by placing it around two pulleys while the center distance between them is reduced. Then the pulleys are moved apart, which puts the belt in high tension. You can also use an idler pulley if you need to control the tension. Power through a belt drive is transmitted through friction. The driving pulley rotates and grips the belt, increasing the tension on the tight side of the belt and decreasing it on the slack side. The difference between the tensile forces of the two sides in the belt exerts a tangential force on the driven pulley. A torque is applied to the driven shaft via friction force. These are some advantages of a belt drive. They can absorb vibrations and noise. The flat belts can be used for extremely long center distances. Friction can be used for mechanical overload protection, and no lubrications required. The shaft center distance variation and shaft alignment is not very critical for V-belts, certainly much less than for gear drives or chain drives. And the video link for V-belt application will give you more details on how they work. This is the basic open belt geometry. The critical dimensions are the center distance between the pulleys, the overall length of the belt, what's called the angle of belt in contact with the driving pulley, theta sub small d, and theta sub large d, which is the angle of the belt in contact with the machine pulley. The formulas for calculating all of these critical parameters are shown here on the slide. And one detail about the center distance is that it does need to be in between the large diameter and 3 times the sum of the large and small diameters in order for the belt to operate correctly. When an input torque T is applied to the small pulley, we have that F1 equals Fi plus Fc plus T divided by D, and F2 equals Fi plus Fc minus T divided by D, where Fi is the initial belt tension, F1 is the tension on the tight side after the load is applied, F sub C is the centrifugal force of the belt, and F2 is the tension on the slack side after the load is applied. And if we subtract equation B from equation A, we get that F1 minus F2 equals T over D over 2, which is the torque over the radius, and the net torque thus is transmitted to the pulley by the difference in tension between the tight and loose sides of the belt. Power is transmitted by the flat belt is the product of net tension, F1 minus F2, and the belt speed V. And expressing power in horsepower and using units of pounds and feet per minute gives that P equals F1 minus F2 times V divided by 33,000 to give you the power in horsepower. The belt speed V is given by V equals pi times D times N1 divided by 12, and that gets you the belt speed in feet per minute. N1 being the rotational speed in RPM of the driving pulley. These are different cross sections that you can find in belts and pulleys. The flat belt is the simplest, but you always have to worry about it sliding off. The round belt is a circular belt with a half-circular cross-section of a groove on a pulley. This does get used for very, very low torque applications and very small belts, as you might find in toys. It's very, very low cost, but it can't handle a lot of torque. The most common belt is known as a V-belt because the belt is a trapezoid where the sidewalls are in the shape of a V. And for applications where you need excellent timing and no slip between the belt and the pulley, you use what's called a synchronous or timing belt. At that point, rather than call the other structure a pulley, we call it a sprocket. Heavy-duty V-belts come in 3 sizes, 3V, 5V, and 8V, where those odd numbers are the numerator of an equation that divides by 8, and it gets you the longest dimension on the belt, which is across the top. In metric, we have roughly equivalent sizes 9N, 15N, and 25N, where the number gives you the nominal top width in millimeters. Here's a step-by-step procedure to design a V-belt drive. Given the rated power and speed of the driving motor, speeds of the driving, meaning the small pulley, and the driven, meaning the output pulley. First, you determine a service factor based on harshness of the application, and you multiply by motor power to get a design power for the system. You select from one of 3 V-belts based on the speed of the motor and the design power. Compute the nominal speed ratio and pulley diameter ratio. Pick the range of belt speeds. Assume an optimal belt speed of 4,000 feet per minute. Use that to calculate the diameter of the driving pulley. And look up standard commercially available sizes of driving pulleys that give you close to the correct output speed when using the computed speed ratio. You'll also get the driven pulley diameter as a result. You then use tables to get a rated power per belt, and you specify the smallest center-to-center distance allowable based on the formula that the center distance has to be in between the large diameter and 3 times the sum of the small and large diameter. You then compute an estimated belt length L from these formulas shown below, which also tells you how to compute the center distance as a function of the total length of the belt. And these formulas also tell you how to calculate the angles of belt in contact with the driving and driven pulley. In step 9, you select a standard commercially available belt length that's closest to the one computed in step 8. You then compute the angle of wrap of the belt on the small pulley, theta sub d, from this formula shown. Determine some correction factors for the rated power per belt from standard graphs, and divide the design power of the system by the corrected rated power per belt to get the number of belts you need. This number is usually a decimal number, but recall that belts only can be purchased and used in integers, so you always round up to the nearest integer for the number of belts to use in your system. Here's an example of how to specify a belt. We're going to solve problem number 7-18 in our textbook. We're going to design a V-belt drive that has the driving pulley on the shaft of an AC motor, which has high torque. The motor is rated at 25 horsepower at 870 RPM, and the drive is to a hammer mill that's to be used 8 hours a day at 310 RPM approximately. A hammer mill shown in these photos is a crusher that can grind, pulverize, and crush a wide range of materials. It's otherwise known as a rock crusher, and it basically employs a large number of hammer blows to large rocks to shatter and disintegrate the material into small rocks. Or you can use hammer mills in agriculture. In this case, we're showing flaxseed powder being created from raw seeds. You determine the service factor from table 7-1. Our design power is 1.5, meaning the service factor 1.5 times 25 horsepower equal to 37.5 horsepower. And we got 1.5 as the service factor from the fact that on the label for the columns, we're using a high torque AC motor 8 hours a day, which is between 6 and 15. And as far as the rows, we see we have moderate shock loading, and directly the phrase hammer mills is shown. So we read across where the row intersects the column, and circled in red is the number 1.5. We then select the V-belt sizes from either 3V, 5V, or 8V, and that's done by determining on the x-axis what is your design power, which in our case is 37.5. You then read up with the 37.5, and you find where it intersects the speed on the y-axis of your motor shaft, which in our case was 870. And where the x and y coordinates meet is an area that is within the region that is defined by the use of a 5V belt. If you were in a region that was for a 3V or the region for an 8V belt as shown in the graph, then that's the one you would use. So you calculate a speed ratio, which is 870 over 310, which is 2.806, and that is the same as the pulley diameter ratio. You then calculate the diameter of the driving pulley at a nominal belt velocity of 4,000 feet per minute, which is in the middle of our range of allowable linear belt speeds. The belt speed VB is equal to pi times small d times n1 over 12, and the motor speed n1 is 870 RPM. And multiplying out, that says that the small pulley will have a diameter of approximately 17.56 inches, but we will have to find a commercially available pulley that's close to that diameter. When we went in this application to look up standard size of driving pulleys, we found one close to 17.56, when we multiplied by the speed ratio, we found that we were well up into the 50s in terms of finding an available large pulley. So we had to back down what would be the small pulley size so that we could find both a small and a large pulley on one chart. And that was done because our goal in the exercise was to try to get the actual output speed as close to 310 RPM as possible. So when we looked at the combination of 38.35 and 13.4 and divided the two numbers, we found that we hit very closely our 2.806 speed ratio, which allowed the 870 RPM of the motor, which is the input speed, to get us a 310 RPM output speed. We then used figure 7-15 for 5V belts to get the rated power per belt. On the x-axis, we had 13.4 inches for the small sheave pitch diameter. We then read up to the curve for 870 RPM input speed and read across to the y-axis and found that our rated power was approximately 23 horsepower per belt. We then used figure 7-17 to get the power per belt for 5V belts, which gets added for the speed ratio. Our speed ratio is 2.8 and our RPM is 870. We then found that the power added to the rated power would be 0.94 horsepower. We need to specify a small center-to-center distance to keep the design compact. And we know that C from formula has to be between 38.4 inches and 155.4 inches. So as a first guess, we said, well, let's try C equals 48 inches, which is closer to the smaller end than the high end. We then compute the required belt length L from formula, and we get 180.8 inches. And we select the standard belt length and recompute the actual center distance because we can't buy 180.8 inches. But in this chart, table 7-2, we can buy 180, and the center distance wasn't that critical. So we select the 180-inch length belt and we recalculate our center distance C, and rather than 48 inches, we're close, we get 47.6 inches. We compute the angle of wrap of the belt on the small pulley from the formula, and we get 149.4 degrees. And we determine the correction factor for the angle of wrap for 149.6 degrees, and we get a correction factor of C sub theta equals 0.92. We determine a correction factor for the belt length using a 180-inch belt and get C sub L equals 1.06 using the curve for the 5V belt. And we multiply our power by correction factors 0.92 and 1.06. And we find that the actual horsepower per belt, instead of being 23, it's 22.4. And the number of belts is our 37.5 horsepower divided by the 22.4 for the corrected power, and we get 1.7 belts. But you can't use 1.7 belts, so you round up to the nearest integer, and that means we're going to have 2 belts in this application, and our pulleys will have 2 grooves each for the 2 belts. Here is a screenshot of an Excel solution to problem number 7-18. The input numbers are in the gray shading, and the output numbers are all the same as in these slides, but I go through it row by row so you can follow along. Here's the second half of the output numbers, also in sequential form, so you can use this general flow in the spreadsheet for your own calculations for your homework. Synchronous belt drives, otherwise known as timing belt drives, have ribs or teeth cut across the underside of the belt. The teeth mate with grooves in driving and driven sprockets, providing positive drive without slippage. Timing belts are most commonly used to connect the crankshaft to the camshaft of an internal combustion engine, so that all valves open and close at precise times. And here's a picture of timing belts used in automobile engines. This photo was taken at the Stony Brook Research Park Advanced Energy Research Center. The timing belt connects the crankshaft and camshaft on the left. You also have a serpentine belt, which is a multi-rib flat belt on the right that connects the alternator, oil pump, water pump, and air conditioning compressor. The alternator is shown on the bottom. Replacing a timing belt on an automobile is a very expensive job, typically $1,000 to $1,200 at a dealership. You normally have to have it done at 80,000-mile intervals, and if you break a timing belt while the automobile is in motion, this can lead to major engine damage. Here's a diagram of timing belt geometry. The belt tension side, in this case, is on the top. The belt slack side is on the bottom, and you need an outside flat idler tension to have an acceptable amount of tension on the slack side. Both sprockets rotate counterclockwise. At least one of the two sprockets has side flanges to prevent the belt from slipping off the sprocket. This one in particular on the left side is made of neoprene. It has a nylon facing, neoprene teeth, and internally within the neoprene backing is tensile cords that are often made out of steel. Split taper bushings in the hub have different bore sizes to fit shaft diameters. The keyway in the split tapered bushing prevents rotational movement of the sprocket and bushing on the shaft, and then the shaft goes inside the split taper bushing. Table 7-4 shows you a list of sprockets available in an 8mm belt. To decode the part number P22-8MGT-20, you have 22 teeth, 8mm pitch, type GT profile, and a 20mm belt width. The 3 half holes in the bushing are aligned with the 3 half holes in the sprocket, and they're used to assemble the taper lock bushing to the sprocket. You also have Table 7-5, which defines different taper lock bushing sizes along with the minimum shaft diameter that can go through them and the maximum shaft diameter. Table 7-6 gives us types and sizes of synchronous belt drives, both in metric and in English, and it shows a general range of available belts. You need to consult the manufacturer's web page if you want an exact list of belts that are sold. Here's a step-by-step procedure to design a timing belt drive. If you're given the application, rated power and speed of the driving motor, output speed, shaft diameters, and center distance, follow this procedure and you will be able to select the proper timing belt and sprockets. In step 1, we determine a service factor using Table 7-8 and calculate the belt design power. We then determine the pitch and calculate the speed ratio between the driving and the driven sprocket. We calculate the design power in the same way as for V-belts. We then determine the pitch using the pitch selection guide, figure 7-27. We compute the nominal speed ratio, which also gives you the pulley diameter ratio. You then select the possible numbers of teeth in the driver and driven sprockets that gets you close to the nominal speed ratio. In step 8, we rule out any sprocket combinations that create interference with nearby parts or can't be used due to restrictions on the shaft diameter. Given a desired range of center distances, we determine in step 9 a standard belt length, and we use Table 7-7 as a guide for the belt length versus the center distance. In step 10, we select the belt width using Tables 7-9 and 7-10 as a reference, and we adjust the base rated power for a length correction factor. We calculate the belt linear speed, designing for less than 6,500 feet per minute to prevent large centrifugal forces on the sprocket, and under 3,500 feet per minute if quiet belt operations required. In step 12, we specify part numbers for the belt, the sprockets, bushings, and a belt tensioner if needed. Here's example problem number 7-4 in our book. Figure 7-29 shows a 20 horsepower electric motor driving a gear pump using a synchronous belt drive. The normal torque motor speed is 1750 RPM, and the gear pump speed is to be 875 RPM. The drive system is mounted on a steel mounting plate as shown in the figure, with slots permitting an adjustment of pump position by plus or minus 0.375 inches from its nominal center distance of 22 inches. The motor shaft diameter is 1.625 inches and the gear pump shaft diameter is 1.375 inches. The sprocket on the pump shaft cannot exceed 14 inches due to potential interference with the base plate. That's shown here. I'll bring you over there with my mouse. If this sprocket gets too large, the outside diameter of the sprocket will hit this base plate. That's what they're referring to. Our pump will operate 16 to 24 hours a day, 5 days a week, and your job is to specify the complete drive system. So step 1 is to determine service factor from table 7-8. Our design power is a service factor of 1.7 times 20 horsepower, which is 34 horsepower. We get the 1.7 service factor from the fact that we have a normal torque AC motor running 16 to 20 hours daily, and our pump is gear driven, which is defined in the lower left corner. We select the 8mm pitch belt part number 8MGT, using figure 7-27. That stems from 34 horsepower coordinate on the x-axis and a 1750 RPM coordinate on the y-axis, which corresponds to the speed of the larger shaft and the speed of our motor. These coordinates intersect in the yellow-colored region for 8mm belt. We use table 7-7 to select 8 possible combinations of sprocket teeth. The reason we have 8 is that the speed ratio of N1 over N2 is 1750 over 875, which is 2. And in the lower left corner, we find 8 different combinations of driver and driven sprockets that have a speed ratio of 2. And we now use table 7-4 to identify all the bushings used by the driver or small sprocket. Our idea here is to find acceptable bushings based on the large and small diameters of the input and the output shaft. In table 7-5, we can rule out small sprockets based on the maximum bore of the bushing. Because the motor shaft diameter of 1.265 inches must be less than the maximum bushing bore diameter, and that's only true for bushing size 2012, which corresponds to driver sprocket sizes 56 and 72. We now use table 7-4 to rule out the driven sprockets based on possible interferences. And that's because the sprocket on the pump shaft cannot exceed 14 inches due to potential interference with the base plate. We could possibly use driver 72 and driven sprocket 144, but driven sprocket 144 is a pitch diameter of 14.437 inches, which is greater than 14. Thus, we are left with the only solution being a driver sprocket with 56 teeth and a driven sprocket with 112 teeth. We use table 7-7 to pick a belt based on restrictions on the center distance, which says that our nominal center distance must be 22 inches plus or minus 0.375 inches. Fortunately, we found a center distance corresponding to a belt and two sprockets of 22.03 inches, which corresponds to a 225 tooth belt. We use tables 7-9 and 7-10 to pick a belt width. We have a 20 horsepower electric motor driving a gear pump using a synchronous belt drive, and the normal torque motor speed is 1750 RPM and the gear pump speed is 875. And we found for an RPM of 1750 that for a 56 tooth small sprocket we have a rated horsepower of 43.2 horsepower. But our design power is only 34 horsepower, and because 43.2 horsepower is greater than the 34 horsepower, the 1800-8MGT 30mm belt running on a driven sprocket with 56 grooves is acceptable. We then use table 7-11 to confirm the rated belt power being acceptable. In this case, our design power is 34 horsepower, and the rated power of the belt must be above 34 horsepower. Well, if we multiply our belt power rating of 43.2 horsepower by 1.2, we get a power rating of 51.8 horsepower, which is much greater than the 34 horsepower, hence our belt is again acceptable. We now calculate the belt speed to ensure it does not exceed 6,500 RPM. In our case, the formula we have shows that the speed is only 2572 feet per minute. And on the bottom of the slide, we show you all the part numbers that we've selected for our design. Here's an Excel summary for example problem 7-4. The input data is shown in gray shading. And here is the Excel summary for the full example showing both the input and the output. In a chain drive, a metal chain consisting of pin-connected links engages mating tooth wheels, which are called sprockets. And a chain transmits much larger tensile forces than a belt. A roller chain has a roller on each pin that provides very low friction between the chain and the sprockets. The pitch is the distance between the two pins of the chain or the teeth of the sprocket. The tension is higher on the side of the chain about to engage with the driving sprocket, is known as the tight side. The slack side is the opposite side of the chain. A metal chain requires constant lubrication from an oil bath for heavy machinery and periodic oiling for light applications such as the transmission in a bicycle. In a heavy machinery application, the chain is constantly immersed in a bath of oil as shown in these diagrams. Chains come in different geometries and metal gauges. You can have double and triple chain strands which provide higher strength. An assortment of roller chain styles is shown in the picture below. Usually the driving sprocket is smaller diameter than the driven sprocket so that speed reduces and torque increases. But there's one big exception, and that's the bicycle. Your legs supply plenty of torque, so you trade some torque for speed to get somewhere fast. On an average bicycle, the gear ratio peaks at roughly 1:1 in first gear, which is for steep hills, and it goes down as you shift up to gear 10, 12, or 15. Roller chain sizes are shown in Table 7-5. The sizes are classified by pitch. Digits other than the last 0 correspond to the pitch in eighths of an inch. And for applications where you're lifting heavy weight with a chain drive, make sure the maximum weight lifted is only about 10% of the average tensile strength of the chain. Some advantages of chain drive are that they require no tension on the slack side, so bearing loads are reduced, and you don't need an idler. Chains don't slip or creep the way flat and V-belt drives do. Chain drives are more compact than belt drives for the same power transferred. They don't deteriorate with age, heat, or oil and grease being made out of metal, and they can operate at higher temperatures than belts. Here's the basic chain geometry along with the equations for L, the total length of the chain, and N1, the number of teeth in the small sprocket, which is in pitches, not inches or millimeters, and N2, the number of teeth in the large sprocket, which is in pitches P. The center distance C can be calculated as a function of the chain length in N1 and N2, and the diameter D can be calculated in terms of the number of pitches, and N, where N1 corresponds to the teeth in the small sprocket, and diameter 1 would be the diameter of the small sprocket. Same goes for the large sprocket, we're using N2 and D2. Here's some design guidelines for a chain drive. The small sprocket should have no less than 17 teeth, and the large sprocket no more than 120 teeth. Your maximum speed ratio for a sprocket pair is 7, and the center distance should be 30 to 50 times the pitch of the chain. The chain length has to be an integer even multiple of the pitch. The arc contact theta 1 of the small sprocket must be greater than 120 degrees for proper engagement of the chain with the sprocket. You put the tight side of the chain vertically up and make sure to avoid excess chain sag on the slack side or the chain could jump off, which is not really fun when you're on a bicycle having to put the chain back on the sprocket. Here's a step-by-step procedure to design the chain drive. Given, you have the rated power and speed of the driving motor, speeds of the driving sprocket, and the driven sprocket. First, you determine the service factor based on the harshness of the application, multiplying the motor power to get a design rated power for the system. You then compute the nominal speed ratio, which also gives you the ratio of the number of sprocket teeth. Select the chain pitch based on rated power, compute the number of teeth in the sprockets, and use the number of teeth for the actual output speed. Then compute the pitch diameters of the sprockets with the equation shown on the bottom. In step 7, we calculate the nominal center distance C in terms of pitches, not inches or millimeters, and you use 40 as the first guess because 40 is halfway between the guideline of 30 and 50 pitches. You then calculate the required chain length L in number of pitches and round off to the nearest even integer number of pitches using the formula below. Recalculate the center distance in terms of pitches using the formula below and compute the angle of wrap for both sprockets. If you want to calculate L and C in the number of inches or millimeters, first get the number of pitches and then adjust for the actual pitch based on what the pitch is in terms of inches or millimeters. So we're going to solve problem 7-38, which is to design a chain drive that has a driving sprocket on the shaft of an AC motor. The motor is rated 25 horsepower, 310 RPM, full speed load, and the drive is to a hammer mill at approximately 160 RPM. This should be a familiar problem because we solved it before for a V-belt drive. Now we're going to solve it for a chain drive. First, we determine the service factor and design power from table 7-17. And that service factor is 1.5 because we're using an electric motor and it's for a hammer mill. And you just intersect the column for the electric motor with the heavy shock row that says hammer mill and read across. The design power then is 1.5 times 25, which is 37.5 horsepower. Our speed ratio is 1.938. Now we're going to select the chain pitch from table 7-16. We use the closest number to our rotational speed of the small sprocket, and 300 is very close to 310. If we were in the middle between two numbers of rotational speed in this chart, we'd be better off interpolating. And we find that we need to select a design power of the chain that's greater than 37.5 horsepower, and the only one on this chart is 42.03 horsepower for the 300 RPM speed rotation of the small sprocket. And this corresponds to 40 teeth. So we're going to use a number 80 chain, which has a 1-inch pitch, and N1 is 40 teeth, and we're going to be using a type B lubrication for the chain. N2, the number of teeth on the large sprocket, is N1, which is 40 times 1.938. We get 77.5, but we can't buy a sprocket with 77.5 teeth, so we round up to 78 teeth. We compute the actual output speed. It's not 160, but it's close. It's 159 RPM. And we compute the pitch diameters of the sprockets in inches. The small sprocket is P, the pitch, which is 1, divided by sine 180 degrees divided by 40, because that's the number of teeth in the small sprocket. And we get 12.745 inches. Use a similar formula for the large sprocket and get 24.835 inches. We calculate L, the required chain length and number of pitches, and we get 139.9, but we must round up to the nearest even integer, so that makes 140 pitches, which, because the pitch is 1 inch, is also 140 inches. And we calculate the center distance from this formula here, where N1 is 40, N2 is 78, and the center distance comes out to 40.04 pitches, which is close to our desired number of 40, and that is equal to 40.04 inches because the pitch is 1 inch. We compute the angle of wrap using our formula shown in the middle and figure out that the angle of wrap of the smaller sprocket is 162.6 inches. That of the larger sprocket is 197.4 inches. You will always find the angle of the large sprocket will be greater than 180 degrees, and the angle of the smaller sprocket will always be less than 180 degrees. And here is our Excel solution to problem number 7-38, showing the input data in gray shading and the output without shading. And this is the second half of the output data.